Okay, we now discuss about minimizing DFA. So what do we mean by minimizing DFA? So suppose you have some regular language. Take this L, which contains sets of all strings, which contains exactly one. So that means strings over. So the sigma we are talking here is 0, 1. Okay, so this is our input alphabet. And this L consists of strings which contains exactly one. So this is a regular language because we have DFA for this, and not just one DFA, this two DFA. So I'll not prove that this thing actually accept this thing, but the point is for a regular language you can have multiple DFAs. Okay. So now if you have many DFAs for the same language, obviously you would like to have the simplest one. So even as a machine this is easier to build, it will cost less. So now the point is this is simpler because this has less number of states. So just talk about the number of states. Okay. Now suppose you construct this. So how can you be sure that this is the DFA with the least number of states? For example, naturally you will ask questions like, so is there any equivalent DFA? So that means that a DFA accepting the same language. So is there any equivalent DFA with fewer states, 1 or 2? So for this particular example, maybe you will consider all DFA with 1 state and 2 state and easily show. But suppose you have constructed some DFA with say 6 state or 10 state, and how can you be sure that there doesn't exist any other DFA with less number of states? You cannot say go over all possible DFAs of say 9 states or 8 states or 7 states, and that is huge, right? So and not only that, so even if you are somehow sure that you will require at least 3 state, so now you can ask, so is there any other equivalent DFA with 3 states? Okay. So that means when you are sure about the least number of states, so do you get a unique DFA for that, or there can be different DFAs with say 3 number of 3 states? Okay. So here you are asking about the uniqueness of the minimal DFA. And finally, we would like to have some kind of algorithm, some kind of recipe to find this minimal DFA. So for example, if this is given, there should be some I mean, at least it's good to have some method such that you somehow transform this into this thing. Okay, so these are the things we are about to discuss when we say minimization of DFA. Now before we do that, we need to brush up some basic facts about relation. Okay, so what is a relation? A binary relation. So a binary relation on a set A is just some pairs of elements of this A, right? So this pairs like x, y in R, and instead of using this notation, when we say relation, we use it like this, right? So x, R, y. For example, say less than is a relation on integers, greater than is a relation on integers. So you can, so this is a relation, and we will also use this x, this not of this R, y. So this means that they are not related. This pair is not here. So when is our equivalence relation? So if it is reflexive, symmetric and associative, so reflexive means it's related to itself. Symmetric means you can switch the order of this x, y, and associative means if x is related to y, y is related to z, then x is related to z. So this is the definition of equivalence relation. And whenever you have an equivalence relation, we can talk about the equivalence class. Okay, so what is the equivalence class? So you take some element in A so take this element x in A, and you take all the y's which are related to x. Okay, so that set we can call the equivalence class of x for this relation R. Okay, so this means this is a subset of this A. Which subset? So it's precisely all the elements which are related to x. Okay. So now again it's pretty easy to show from this properties that if you have x related to y, then their equivalence classes are same. So you can have different elements here. So this sort of different representation of the same equivalence class, but the equivalence class is same. So this is important. So somehow, many times we use two different elements here, but the equivalence class will be same if and only if this x, y are related. And similarly, if x and y are not related, so then this equivalence class will be disjoint. Okay, these almost immediately follow from the definitions. So yeah, so if you take two equivalence classes, either they are same or they are disjoint. And not only that, if you take all the equivalence classes and their union, so you generate this whole of A. So in fact, if you take that means all the equivalence classes here. Okay, so the union of all these sets will generate A. So that means this thing is actually a partition of A. So if you have say this whole circle is A, treat this as a Venn diagram. Okay, so this equivalence classes will be like this is equivalence class, this is equivalence class, this is equivalence class. So this is just the idea of partitioning a set into disjoint classes, right? So and formally, what is partition? So partition is partition of a set A is a family of subsets of A. So this is the power set of A. So that means elements here are subsets of A. So this P is a family of subsets of A, such that the main property is that if you take all the subsets here and take their union, then you get back A, and they are, if they are not equal, then they are disjoint. Okay, so yeah, so here you can say this is x, this is y, this is some z. So either you have x equal to y, and if that it's not, then they are disjoint. That's a property of partition. And one also very technical thing is that this partition should be non-empty. So each partition, each class in this partition should be non-empty. So that's a technical requirement. So yeah, so if you have this equivalence class, two elements belong to this same class if and only if they are related, and if they belong to these two different class, that means they are not related. So you see that this thing that if you have a relation, then you take the equivalence class and that will give you a partition. And similarly, if you have a partition, so then you can define this R like this. So given the partition, you say that some two elements are related if they belong to the same class. So that means if you have equivalence relation, then you have a corresponding partition. If you have a partition, then you have a corresponding equivalence relation. So they are just same thing, just this two different way of looking at the same thing. It's partition and equivalence relation are same in the sense that one is related to other, and there's a one-to-one correspondence. Okay, and then we have something called refinement of equivalence relation. So you take two equivalence relations, so R and R prime both are equivalence relation on the same set, say on A, and if this is the case that X is related to Y in this R prime, implies that X is related to Y via this R. So if that happens, then you see that if you take equivalence class of X in R, so that will be union of some equivalence class in R prime. Okay, so it's precisely this union. Okay, so what is happening here? If you look at this picture, see, this is the partition for R, okay, and this is the partition for R prime. Why? Because if they are related in R prime, so they should be related in R. So here you see that these are this x4, x5, so they are related here, so they are also related here. But the other way is not true. So if you have say you have this x1 and x2 which is related here, but it doesn't mean then that they are related here, right? They are different. And this is the contrapositive of this thing. So this means that if they are related here, then they are related here. The contrapositive here is that if they are not related here, then they are not related here. So say if you take this to example, they are not related here, so they are not related here. So what is happening is, so from this you can see that we already said that any equivalence class of R is union of some equivalence class of R prime. So that means if you take a class in R, so just take this, so this in R is union of some, so that means here you are splitting this class, right? So you are just taking this thing and splitting it. So now this becomes the union of this part and this part. So similarly here you are taking this and splitting it into three parts. So this becomes the union of this. So this justifies the definition refinement. So if it is like a sieve, it's like you're going for finer and finer sort of partition. So yeah, and another thing I should say here, that this definition of index of an equivalence class. So if you have a equivalence relation, correspondingly you will have a partition defined like this, and the number of equivalence classes, the cardinality of this set, so cardinality of this partition, so the number of equivalence classes is called the index of equivalence class. So now for a general set and general sort of equivalence relation, this index can be finite or infinite. So this index is finite or infinite. And even it can be uncountably infinite or whatever. So but yeah, so this index is the cardinality of this thing, to speak. Now you see that here, as I said, it's just taking this thing and splitting this into finer chunks. So that means the index here is at least as large as the index of this thing. So R is a refinement of itself. So in that case, this equal. So yeah. So when is this equal? So say that they are finite. If they are infinite, then equality doesn't make much sense. But say that both of them are finite, and in general, so this will be, this can't be more than this. But when are they equal? And if you have this refinement, so yeah, so R prime is a refinement of R, and suppose you have this equality. So you can have equality only if R is equal to R prime, right? So I am saying that if R prime is a refinement of R, and if you have, say, index of R is equal to index of index of, say, R prime. So if you have these two things together, so then that means this R must be equal to R prime, right? Otherwise you will have more number of partitions here. So this is the property that we are going to use, that if the index are equal, then they are same, provided that this R prime is a refinement of R and the indices are finite. Okay. So now we come back to this Dfa minimization problem, and the thing is, here we are only focusing on Dfa, and that too with total transition function. So throughout this thing, the transition function is total. Okay, there is no other ways about it. So consider some language, okay, some language L which contains, say, this 001, 101, and say other strings are of length 4 or more. So it doesn't contain any other string of length 3. It doesn't contain any string of length 2 or 1 or 0. So it contains these two strings of length 3 and some other strings of length 4 and something else. So we are not even specifying it completely, just this property. Okay. So we do not know whether L is regular or not. I mean, it can be regular, it cannot be regular, depends on what you have here in the remaining part. But if L is regular, okay, if L is regular, and say this is a Dfa and that accepts L, so is it possible that okay, I made some mistake, oh no, sorry, no mistake. So yeah, is it possible that these two states are equal? Okay. So you do not know what L is, but all I am saying is that suppose L is regular, so that means there exists some Dfa M, but whatever Dfa you consider, I am asking that is it possible that in that Dfa, so you start with this Q0, and then you have this 0, 0, you reach some state, and then you have some 1, 1, some other state. So is it possible that you reach the same state? Is it possible? So now you see this string is in your language, right? So that means from this 0, 0, if you process one more 1, okay, so if you process one another 1, so then you reach some final state. So this thing should be final. But what about this thing? So if you do this 1, 1 and process another 1, so then this 1, 1, 1 should be in your language, but 1, 1, 1 is not in your language, right? So that means this thing cannot be this thing. So this thing must be something else. So this thing cannot be this This must be something else. It is something such that if you process another one, you get to a non-final state. This is final, this is non-final, right? So even without knowing what the language is, okay, we concluded that it must have at least two states, okay, and it may not even be regular, so that means it may not be handled by any finite automata. If it is regular, then finite states are okay, right? If it is not regular, you cannot handle it using finitely many states, so it may require infinitely many states. But at least we are arguing here that it requires at least two states, right? So these two states, this one and this one, they cannot be same, right? So yeah, this is a clever way to attack this problem, because you see, we do not fully know what L is, and we are not talking about any specific DFA. So this argument works for any DFA that you choose. So that means any DFA you can think of for accepting this L, it must have at least two states. So why did this argument work again? So this x, say 0 0, and this y, say 1 1, so that leads to different states. Means if you start with this 0, so it leads to this thing and it leads to this thing. So there that leads to different states, because there exists some z such that this xz is in L but yz is in not. So what is z here? So z here is just this 1. So in this example, this z is just 1. But you can have other strings here also, right? So you can use the same argument there. So if you have some z which is of length, say 4 5 6 whatever, so instead of a single transition you will have a path from here to here on z. Instead of a single transition here, you will have a path from here to here on z, and again, so this will be a final state, this will be a non-final state. So again, this will mean that these two states must be different. So yeah, this is the thing that we used, that we found some z such that xz is in L but yz is not in L. Okay. And why is it related to DFA minimization? Because as I said, we need to answer questions like how many states do I need in the minimal DFA. So this sort of argument will tell you that okay, you need at least 5 states, at least 6 states, something like that. So you at least have some lower bound on the states on the minimal DFA. So motivated by this thing, we define a relation RL on the set of strings. So this x RLY, if there for all z xz is in L, if and only if yz is in L. So it's like the opposite of this thing. So here we are trying to say that this x and y are not related, so they are somehow different. Okay, so they are equivalent if this happens. So there exists some z such that this happens and this doesn't happen, so we take the opposite of that, like no matter what z you take. So this is in L if and only if this is in L. So either you have this in L, this in L, or this not in L, this not in L. You do not have that this is in L and this is not in L. So for all z this happens. So this is the relation we define, motivated by what we did here. Now see, here we are talking about DFA and the transition function of DFA and all, but if you just look at this definition, just now forget about this part and just look at this definition. So this definition works for any L, whether it's regular or not. Okay, regular or not. Even for non-regular language, you can define an RL. So whatever that RL will be is a different thing, but we can define RL for any L, right? Because this definition does not require us to consider any automata. See, this definition is only based on L. So this L is completely defined in terms of L only. So for any L, we define this relation. So x RL y if and only for all z, xz is in L if and only yz is in L. So so this part here, for all z this should happen. Now when we are talking about a regular language L, okay, so what we did here, so we talked about a regular language L, and then we considered a DFA M which accepts that L, right? So L is L of this M, where we have some DFA M, and then we can define this relation Rm on sigma star. So x Rm y if this x and y leads to the same state starting from Q0. So this is more like what we did here. So it looks like kind of the same thing here. The importance of doing this is we are now eliminating the M altogether. So this is completely defined in terms of L, but here we are considering a particular M, okay, and this is regular. This may not be regular, so this is regular and we are considering a M, and here we are saying that they are related if they lead to the same state. So here we argued that they will lead to different state. So again, this is like they are saying that they are not related, so they are related if they lead to the same state. Okay, so now just stop and completely make yourself comfortable with this two relations, so these definitions, because in the rest of the slides we will use this hundreds of times. So all the proofs that are going to come will just use this definition. Okay, so now this definition, as you can see, it is dependent on this particular choice of M. So as I said, there can be multiple DFA for this L accepting the same language. So suppose you have two DFA M and M prime both accepting the same language. So this LM is LM prime, but this Rm depends on this particular choice of M, right? So this Rm is not equal to Rm prime if M is not equal to M prime. Okay, so this is important. This is tied to a particular machine where this is about the language itself. Okay, so the argument that we gave here is that if this is true, like if we have a Z such that this is in L and this is not in L, so that means they are not related by RL, so that means they cannot lead to the same state. Okay, that's the thing that we proved here. So that means if they are not related here, they are not related here. So in the contrapositive form, what will mean that if they are related here, that implies that they are related here. So you can see that this is refinement of this relation. Okay, so the definition of refinement that we had here. So if this implies this, then R prime is a refinement of R. So here this implies this, that means this Rm is a refinement of RL. Okay, so that immediately tells you what the index of so the index of Rm can't be less than the index of this RL, right? It immediately tells you that. But the thing is, here we are talking about a regular language, and okay, later we will see a similar sort of thing, but there we do not mention that this is a regular language. Irrespective of that thing, we prove something like that. So there's a difference in that proof. It doesn't assume a priori that we are dealing with regular language. Okay, so now we need to define we need to just mention this thing. So you already perhaps noticed that this RL and RM are equivalence relation. So because they satisfy reflexive, symmetric, and associative property. And these are immediate from this thing, right? So just if you see this definition, this x RL x, right? Because here you can replace this x with y with x. So yeah. And again, you can just switch this x and y here, so they are symmetric and associative because xz in L, if and only if yz in L, if and only if some y prime z is in L. So these properties they just immediately follow from this definition, and similarly for this Rm. Okay. There's nothing to prove there, and as I said that if it is a regular language and accepted by this M, then this implies this, and that means Rm is a refinement of RL. But as I said, later we will prove a similar kind of thing, but not assuming that this L is regular. So another definition that we need is the definition of right invariance. Okay. So a relation, equivalence relations. So in order to talk about right invariance, we should start with the equivalence relation, say R, on a set of strings. So far, this equivalence relation or refinement that works for equivalence relation on any set. Now, in order to talk about right invariance, we need equivalence relation over strings, okay? Because we need concatenation in the definition. So this is right invariant if this happens, that for all z, x is related to y implies that xz is related to yz for all z. Okay. So if this xy are related in R, so that means now I can put anything after x, and if I put the same thing after y, so that thing should be also related to this thing. So if that happens, then we say that this R is right invariant, and immediately you can see that this RL and RM are also right invariant. So it's immediate from here, right? So if you start from Q0 and reach the same state after this x and y, so this means that you start from Q0, and after something you you process x and you process y and you reach the same state. So that means after this, no matter what z you put, so you reach the same state, right? So you can put a z here, and similarly here also, right? For all xy this happens. So if you put some, say, x z prime and y z prime, so that goes here. So instead of x and y, you have, say, some so x z prime z and y z prime z. So that is also, you can club this z prime z together. So it immediately follows from this definition. So I'll not. There is nothing to prove. If you are not comfortable with this thing, just stop this video, take a paper and pencil, and just from this definition verify that it satisfies the definition of right invariance, and it satisfies the definition of equivalence relation. Okay, it's just it's very childish to do. So do it yourself if you have any confusion. Okay, so the main result that we are going to prove is this theorem. Okay, it's named after Myhill-Nerode, Myhill-Nerode theorem. So it says that these three statements are equivalent. So what are these three statements? That this L is regular. So L is over some alphabet sigma. So it is accepted by finite automata. That means it's saying that it's regular. So this statement is equivalent to what? So L is the union of some of the equivalence classes of a right invariant equivalence relation of finite index. So it's a long statement. We break it down. So equivalence relation of finite index, right? So that means you have a partition corresponding to that thing, and that partition has some finite index. So you have some 4, 5, 8, 12, 100, but some finitely many equivalence classes. And L is union of some of these equivalence classes. So union of sum of the equivalence classes. So what is this whole thing? So this whole thing is a partition of sigma star. So that means this together contains all the strings, right? So together it gives you a partition of sigma star. It's a equivalence relation on this set. So now L is just union of sum of this thing. So for example, say you take this and this. So this is a subset of sigma star. So this subset is say is L. So this is what it says. So it says that this and this is equivalent. So it is regular if and only if L can be seen like this. And this says that the index of RL is finite. RL is of finite index. So we have already defined L, this RL. It's same like this X RL Y if and only if for all Z this XZ is in L, if and only if YZ is in L. So it's the same definition that we gave here. It's this definition. Okay. It defines RL and says that RL is a finite index. Okay. So, and the theorem says that all these three statements are equivalent. So if you have any one, then the other two is implied. And the way we will prove this is we will prove that this one implies 2. Then we will prove that 2 implies 3, and then we will prove that 3 implies 1. So if I do that, then equivalence between everything is proved. Why? Because 2 implies 3, 3 implies 1, so 2 implies 1. So 3 say 1 implies 2 implies 3, that means 1 implies 3. And 3 implies 1 is direct here, and 2 implies 3 is here, and 3 implies 1 implies 2, that means 3 implies 2. So 2 implies 3, 3 implies 2. So everything is proved in this, if we prove in this 3 way. Otherwise, when we are trying to prove equivalence of 3 statements, if you just want to do in a haphazard manner, then you have to prove many more, because you have three statements and you are trying to prove that these are equivalent and these are equivalent and these are equivalent. So there is actually 6 direction to prove, but if you can just systematically prove that this implies this, this implies this, and this implies this, then with only 3 proof you have accomplished this thing. Okay. So we first address the first part. So 1 implies 2. Now before starting, we should say that given a regular language L, so we can take a DFA M, and as I said, throughout this talk, our this delta will be a total function. Okay, it's a total transition function. So you take this thing, and without loss of generality, we can say that all the states are reachable from the start state. Reachable means you can follow some array, some edges to reach to this state. So if it is not the case, so suppose instead of this thing, you have, say, this DFA. Okay, but you see that you cannot reach this state starting from here, because there is, so from here you can reach any one of this state, but from here you cannot go here because it's only in this direction. So if this is the case, then all this unreachable state, you can just remove that from your DFA. You can just remove this part. So even if you do that, your language doesn't change, right? So without loss of generality, we assume that all the states in your DFA, so for all states, there exists a string W such that you can reach this state if you process this string starting from Q0, right? So here you can reach processing 0, here you can reach processing 0, 1, here you can reach processing 1, here you can reach processing 1, 1, here you can reach processing 1, 0, and so on, but you cannot reach here processing any string. So if that is the case, then you just remove this state and the associated transition. So this transition and this also, these are all gone. So this whole block is gone, and that doesn't change the language. Okay, so without changing language, we can just remove that part. So yeah, from now on we will assume this property, that for any state there is some string such that you can reach that state by processing that string from Q0. This is the crucial technical requirement. Okay, now you remember this was the definition for this Rm. Okay, so this is related to y in Rm if they lead to the same state starting from Q0. Okay, so what are the equivalence classes of this thing? So what was the definition of equivalence classes? So the equivalence class of X is all the y, the set of all y that is related to X. That means set of all y such that it leads to the same state as this one, right? So that means it has, so you take some state Q. Okay, so this Q is reached by some string. So that means this CQ, so we are taking all the strings such that you can reach this state Q by processing this W. So this means that this CQ is not empty, right? So this assumption that we made, that there exists at least one string such that this happens. So this tells me that this CQ that we are defining, so this CQ is CQ is not empty. Okay, and this tells you that this CQ is actually a equivalence class of this relation, right? Equivalence class of what? You take any string here, Okay, so you take any string w in CQ, so then the CQ will be equivalence class of this thing, right? So w led to this q, and all other strings in this CQ also led to this thing q. So that means this is satisfied. So this CQ is equivalence class with this representation of this relation Rm. Okay. Again, if you are not comfortable with any of this equation, you just stop the video and try to read this thing and just work this out. Okay, glossing over will not do, because we have lots and lots of proofs after this, so everything should be absolutely clear from the very beginning. Okay. Okay, so these are the equivalence classes, and we showed that this CQs are not empty, and if we take union of this thing, if we take union of all these CQs, so that will give you all the strings, right? Why? Because you take any string, you process it, you are supposed to go to some state, because this is total, right? You do not get stuck. So you process any string, you are in some of this state, right? So for any w, that w will be in say CQ for some q. Okay, for any w, there is some q such that this is here. And what is this thing? This is just this. So you process this thing, and this is the thing. Okay. So that means if you take the union of this CQ, that gives you all the possible strings, right? So that means this CQ is a partition of this thing, and what partition? This is precisely the partition corresponding to this equivalence relation, as we said. That this tells you that this is actually a equivalence class of this relation. So if you take this, so this is the partition for this equivalence relation Rm. Okay, so each of this statement is very crucial. So again, you just make sure that you fully understand why this is true, right? Now, what is the language itself? So the language consists of all the strings which can lead you to this state or this state or this state. So final states, right? So you take all these final states, and you take the union of the set of strings corresponding to this, this and this. So that is the language. The string is either takes you here or here or here, and all the strings that takes you here is say CC, all the strings that takes you here is CE, all the string that takes you here is CD. So the language itself is just union of CC, CD, CE for this thing. Okay. And what is the index of this Rm? So these are the equivalence classes. How many equivalence classes? So the equivalence classes are one-to-one correspondence with the state itself, right? So the number of state is the number of equivalence classes. The index of this thing is just the number of states, right? Okay. So we have a bijection between this Q and this capital Q to this partition. Okay. And for this example, these are worked out, because you see when can you go here. So you can go here, and if you then go here, then from here there is no way to get back to this thing, or if you take this again, there is no way to get back to this thing. So starting from here, you can get back to here if you just process even number of zeros. This. So this is a 0 0 star. Okay. So this C is then you can process some even many zeros, then take a 1. So this CC will be 0 0 star 1, This b is what? B is odd number of zeros. This 0 or 0 and then 0 0 then 0 0. So this odd number of zeros is just 0 0 start 0, and then if this is 0 0 start 0, if these are the string that leads here, then you add one more 1 and then you go here, so you just put another 1 here, so you have all the strings which corresponds to this. So you add just one more 1, so then you have some string here, but it also can come from this side, but this we have already said that this is 0 0 star 1. So anything here is either this and another 1 or this another 1. So CC is this and after this another 1, or D is this thing and after that's another 1. So if you do that thing, so you get something like this. Okay, and then you can have some 0 and 1 after that. So anyway, so these are the strings, and the point is, if you take the union of everything here, okay, so union of all the strings if you take, so that together will give you all the strings. So if you take union of each of this thing, you will just get 0 1 star, all the strings, right? And what is this language L? So this is just the union of this thing, this thing, and yeah, this thing. So if you just take this plus this plus this, so that will be your language, right? Okay, so now this gives us the proof of this 1 to 2. So it says that what? If L is regular, then we can do this. So if L is regular, then L is the union of some equivalence classes of a right invariant equivalence relation. So what is this right invariant equivalence relation that we are mentioning here? So it's nothing but Rm, right? So this right invariant equivalence relation here, so this is actually just Rm, right? So this Rm that we define, and as you saw, the L itself is just union of some of the equivalence classes, and it has finite index because the index is precisely the number of states in this M. So that is finite. It's finite automata, right? So this part is proved. So just to summarize, what we did here is this thing that we showed that if we take all the strings that lead to some state q from q0, so these CIs are precisely the equivalence class of this equivalence relation Rm. Okay, so this thing is the partition corresponding to this Rm, and that gives us a bijection between a state and this set CQ, and so this CQs, so instead of just the name of this state, we can just take this thing as our state. So you see that this thing is this equivalence class, so we can take this equivalence class here. This C is this equivalence class, so we can take this here. And as I said, you can have two different things, say x and x prime, such that you have the same equivalence class, and this happens if and only if they are related, right? So here we are talking about this Rm, so that means yeah, this thing. So in that sense, these are equal because they both belong to the same. So see, epsilon belongs here and also 0 0 belongs here, so they are equal. And similarly, this is equal to this is equal to this, and so the states are actually, you see, this equivalence classes of Rm. And what are the transitions? So the transitions are of this form, right? So if you have some W which leads to this state, so now this is the state which you can reach by processing W. So then if you process another symbol A, then you go to a state corresponding to this. So okay, so you go to this state, so this is also an equivalence class. So it's quite clear from here, from sigma, from epsilon, you take 0 and you go to 0. From 0, you take 0 and you go to 0 0, which is same as this epsilon. Okay. Similarly, from here, from 0 you go to 0 1. From here you go to 0 1 1, but this is also equal to 1 1. You can start from here, take 1, go to 1, and take 1 and go to 1. So this is the transition that that is there. So this is what is happening, and we will use this picture in the part from 3 to 1. So this Myhill-Nerode theorem, so this 3 to 1 part, so from there we will again use this idea. Okay. Now this 2 to 3 is quite easy. The only thing is that if you see this theorem, L is union of some equivalence class of right invariant equivalence relation, whatever. So this 2 doesn't say that L is regular, okay, and this also again doesn't say that this is regular. So this is what we have for this 2 to 3 part, that if L is the union of some equivalence classes of a right invariant equivalence relation R, a finite index, then RL is a finite index. So I cannot say that this R is Rm because there is no M here, right? So it just says that it is union of some equivalence classes of right invariant equivalence relation R. Okay, so then we prove that RL is a finite index. We can have RL, so because RL is completely defined in terms of L, right, that we said before. So yeah, this part is important, that even here we are not considering any TFA. And it's just immediate one-line proof because suppose they are related here, so X or Y. So by right invariance of R, so this is right invariance, right? And what was the definition of right invariance? This was the definition, that if X, Y are related, then for all Z, X, Z is also related to Y, Z. So by this right invariance, for all Z, we also have this, and this happens if and only if this happens. Again, this is true for any equivalence relation, right? So their equivalence classes are same if and only if they are related. Okay. Now, since L is union of some equivalence classes of R, okay, so if W is in L, then this entire equivalence class for W is also in L, right? So this L, whatever we are talking about, it is union of some of the equivalence classes of this R, right? And this W belongs to this obviously this equivalence class, right? So now if this W is contained in L, so that means this whole thing is also contained in L, because L is union of equivalence classes. So yeah, so that means what? This is in L if and only if this whole thing is in is a subset of L, right? But this is equal to this thing, so this means that this thing is a subset of this thing, and by this we have that yz also belongs to L. So this gives you what? That yeah, so this gives you that for all z x z is in L if and only if yz is in L. So what is this? This means this is precisely the definition for this RL, right? So here we started with the assumption that x are y, and we ended up here. So x r y implies x r l y. So this is a refinement of RL. Okay. So now if this is a refinement, so by this you see that the index of this relation in the right side, so that is as most at most is the index of this thing here. So that means index of RL is at most equal to the index of R, but this R is a finite index. Okay? R is a finite index. So that means that the index of RL is also finite by this thing. So this is just the one line proof for this 2 to 3 part. Okay. So the next thing is to prove this 3 to 1. Again, that is pretty straightforward by what we have done so far. It may look slightly complicated, but anyway, so this is the thing that if RL is a finite index, then L is regular. Okay. So that is what the third part is, that if RL is a finite index, then L is regular.